This presentation on hydraulic directional valves is the fifth in a series of 8 which provides a comprehensive introduction to hydraulics, the science of fluids under controlled pressure. I'm Paul Cook for Sperry Vickers. Directional valves are often classified as poppet type, rotary type, and probably the most commonly used, the sliding spool type. This is the poppet type check valve, with its poppet held on its seat by a light spring. Flow into the outlet port adds to the spring load, preventing reverse flow. Flow to the inlet port overcomes the light spring force, usually about 5 psi, and flows freely through. Here we have another check valve, but with a difference. It has a small orifice through the poppet. It permits free flow in one direction and a restricted flow in the other. This valve is called, how did you guess it, a restriction check valve. There are times when we need to have reverse flow through a check valve, so we add a plunger, which will unseat the poppet when we apply pilot pressure. Now it's getting easy. This is a pilot-operated check valve. Some people just say PO check. The rotary valve we mentioned is not seen too often these days, so we'll just take a quick look. It has a pressure port, a tank port, and 2 cylinder ports. Passages through the rotor interconnect the porting, so we can extend and retract a cylinder or drive and reverse a hydraulic motor. When the rotor is centered, all ports are blocked, and the unit it controls cannot move. Now, on to sliding spool valves. This shows a sliding spool in a body that has 5 ports. 2 of them are tank ports. Usually you'll find they're connected together within the valve body, so there is only one line going back to tank. In this particular case, the 2 lands on the spool, they're the big sections, are so wide the tank ports are always blocked off from the cylinder ports. So we have only 2 possible flow paths, pressure to port A or pressure to port B. Only leakage oil goes to tank. Now in this illustration, we've made the 2 lands on the spool narrower. Now when pressure is open to port A, port B is open to tank. Then, upon shifting the valve, pressure is open to B and A is open to tank. With 4 flow paths, this valve could be used to actuate a cylinder or a motor. It's this ability to modify the spools and obtain different flow characteristics that makes this type of valve so useful. So far, we've shown the spool-type valves in their 2 shifted positions. What happens when the spool is centered in the body is often the most important condition of all. This illustration will enable us to see the wide variety of center conditions available, and perhaps, with a little explanation, why they are required. Our first spool is called open center. It has very narrow lands, which when centered in the valve body, permit oil to flow freely between all ports. Shifting the spool to the right or left connects the pressure port to one cylinder port and the opposite cylinder port to tank. It could be used to operate a hydraulic cylinder or motor in either direction. When centered, the system pressure would drop to what little it takes for the pump delivery to flow freely through the valve to tank. With all ports open to tank, a cylinder or motor could be moved freely by some outside force. This closed center spool, as you might expect from its name, has all the ports blocked in neutral. Cylinders or motors could not move, except, of course, for the small amount of leakage between the valve spool and body. The pump flow would also be blocked, and system pressure would rise to the relief valve setting, unless oil was being used in another part of the system. That, incidentally, is the advantage of a closed center spool. The pump can be used for more than one operation. Here's a spool with one narrow and one wide land. It doesn't have a name, so we just call it a Type 1 and indicate it by the number 1 in the model designation. With one cylinder port blocked, we can support a load on the actuator, yet unload the pump and the opposite cylinder port to tank. When the pump is unloaded, we'll save energy, so we do it whenever we can. Now here's a case where we want to support a load as we did before, but the pump flow is needed for other operations in the system. One cylinder port is blocked by the wide land on the spool. The other is open to tank. But the pressure port is blocked, making the pump flow available right up to the relief valve setting. We call it a Type 3 for want of a better name and include the number 3 in the model code. Sometimes we want to be able to use the pump delivery elsewhere, but must be able to move the actuator manually for setup purposes or some similar reason. This spool, our Type 6, makes it possible by blocking the pressure port but leaving both cylinder ports open to tank. Now remember this one, because we'll be using it later. If we've left out any combinations, you could probably figure out how to make them yourself by changing the width of one or the other, or both of the two center lands on the spool. Remember though, the two shifted positions cannot change. When pressure is open to one cylinder port, the other must be open to tank, and vice versa. This configuration has both cylinder ports blocked, but the pressure port is open to the tank port in the neutral position. To make this one, we use a hollow spool which has 3 lands, a wide one in the center and 2 narrower ones just outside the cylinder ports. This blocks each cylinder port, but holes in the hollow spool let oil coming into the pressure port flow freely through to the tank port. It's called a tandem center. Now this spool permits valves to be piped in tandem, where oil can flow through 2 or more valves in a series and freely back to tank with all spools in neutral. Shifting any valve in the series will direct oil to and from the actuator it controls. Conventionally, valves are piped in parallel, as we can see in the circuit. That means the pump delivery has a choice. It can go to either of the 2 valves, but the pressure port of one must be blocked in order to use the other. Piping valves in tandem, as we have here, allows the pump to be unloaded when neither one is being used. While this affords some energy savings, other limitations prevent its universal use. So far, we've just taken it for granted that these valves had to be shifted from one position to another, with no mention of how it might be done. In the check valve, it was the flow of the oil itself which opened or helped close the poppet, depending on which port it entered. In days gone by, most valves were shifted manually by means of a lever attached to one end or the other of the spool. Springs or detents would hold them in their neutral position. Well, we still use springs and detents, and in some cases cams or levers, but most of today's more sophisticated machinery is controlled electrically using solenoid-actuated valves. This enables us to use push buttons, limit switches, and indicator lights to ease the burden of the machine operator. Solenoids are at their best when used with small valves requiring relatively little force to shift them. Knowing this, most valve manufacturers today use small solenoid-operated valves to control larger valves hydraulically. They're called pilot-operated solenoid-controlled valves. This valve is so universally used that a closer look is in order. Let's start by looking at the mounting surface. These 2 large openings are the cylinder ports. They're identified by the letters A and B cast on the housing. Another way is to remember that these 2 smaller ports lead directly into the cylinder ports and may be used for gauge connections. We know from our spool discussion that the pressure port is located between the cylinder ports, so it must be here. This one is the tank port. The 2 small ports here and here are the pressure and tank ports for the pilot valve. That's the little one on top. We don't see the cylinder ports of the pilot valve because they're connected through internal passages to each end of the spool in the large valve body. In this way, small solenoid-operated valves can control valves large enough to handle several hundred gallons per minute. Most valves of this kind require a minimum of 50 psi for pilot pressure. More often than not, this pilot pressure can be obtained through an internal passage connecting the pressure port of the main valve with the pressure port of the pilot valve. When this is not possible, pilot oil is obtained from an external source, piped into the small port we saw on the mounting surface. Here we have some units which we can use to review. This is a right-angle check valve. A pilot-operated check valve would have a plunger to unseat the poppet when reverse flow is required. Now, shifting the handle manually or mechanically causes the spool in this rotary valve to rotate and direct pump flow to one or the other of the cylinder ports while opening the opposite one to tank. Its small size made it useful as a pilot valve until solenoid-operated valves became more prevalent. And this type of valve will handle up to 5 gallons per minute at 5,000 psi. It utilizes wet armature solenoids for long service life, and as you can see, is frequently used as a pilot valve. Each of these spools can be fitted into this body to perform the various functions we've discussed. Here's the open center spool, the closed center spool, the Type 1, the Type 3, and here's the Type 6 that we ask you to remember. It's used as the pilot spool in all spring-centered valves. And finally, here's the tandem center. Now, this valve was not included in our discussions. Actually, it's a bank of manually operated directional valves containing spools similar to those we've covered. They're assembled together for the convenience of the operator in mobile applications. A complete bank usually includes a main system relief valve, 2 or more individual sections, and in some instances, relief and replenishing check valves within each section. It's often possible to control the many functions on a large piece of mobile machinery with a single bank of valves of this type. Okay, that covers directional valves, which control the direction of the flow in the hydraulic system. And thus completes Chapter 5 in our 8-part training series. And of course, thanks for your interest in hydraulics. I'm Paul Cook for Sperry Vickers.